So welcome to my talk towards the Modelica OPC UA library for industrial automation. Now, what was the motivation? OPC UA is a standard for interconnectivity in the industrial automation world, and it is often named as a technology for future automation systems. Now, the idea was, okay, connect the Modelica world with OPC UA for enabling different kinds of applications with those future automation systems. So you want to play in that arena. But what exactly is OPC UA? Well, it's a platform-independent standard for multi-layered architecture developed by the OPC Foundation. The OPC Foundation is the group that also standardized the highly successful OPC standard that is used a lot in the automation world. And OPC UA is the designated successor standard. Now, the core of it, so that's the red box, is the ability of semantic information modeling, which allows, for example, an object-oriented style of modeling devices, including hierarchical composition, object types, type hierarchies, instantiation, and relations between objects. So that are the building blocks or the meta model of OPC UA. And on top of that, you can build something which information model, which is a little bit akin to libraries in traditional programming languages. The orange box is the core information model. This is the one that is standardized by OPC UA itself. So it's a little bit like a standard library. And then it allows you to talk about analog data, alarm states, and a lot of other things. And now the clue is you can extend it with so-called companion specifications for domain-specific standardization efforts. So different interest groups, for example, for robots, can come together and say, okay, for our domain, we want to standardize something on top of OPC UA. So how, what elements does a robot have, and how to access these elements and so on. And then they can go together, create this companion specification and publish it under the umbrella of the OPC UA Foundation. And for you as a programmer, that is then good news, at least if other vendors pick that standard up, because you can program against the specification and your program will run for any robot. Now you can also have your own information model for your specific needs. So you can have vendor-specific information models. Now this is all rather abstract and we need to access the data somehow. For that, we have got our client-server model, which is used. So the client asks the server, what data do you have? And the server also provides ways to access this data, to execute methods on the server. You also can be notified by the server if data changes or if there's an event. We still have the protocol. Since this is a layered architecture, you could define your own protocol, but there are already protocols defined by OPC UA, the binary TCP protocol, which is the more important one, and the web service-oriented one. There's also another way to access data, that's the PubSub, so the publish subscriber model, but that has entered the standard more recently, and it's interesting, but it's out of the scope of this talk. What kind of Modelica-based applications do we want to enable? Well, first, component simulations. In that case, the simulated component has an OPC UA server instance, and that mimics an OPC UA server of an actual system component down to some desired level of fidelity. And that is useful for hardware in the loop or virtual commissioning. The other is interactive simulation and control. In that case, the simulation has an OPC UA client instance, which interacts with physical hardware components. And applications are process visualization, health monitoring, or model-based high-level control tasks. Now, we are not the first that try to bring together OPC UA with Modelica world. In OpenModelica, there's a probably not very well-known feature that you can start it with an embedded OPC UA server. The goal is quite different. The goal is, so it's not a library, it's integrated into the tool, and you can control your simulation using the OPC UA protocol. So you can start your simulation, stop the simulation, step forward, and read variables from the simulation. Then there exist client libraries, which share similar goals to our own approach. There's from Wolfram, the OPC UA Modelica library, and from Simulation X, the OPC UA client Modelica library. To the best of my knowledge, they currently don't support the server side, but the client side is, from the ideas, I think what we want to enable, quite similar. Now to an overview, this is on the left side a package view of the library. The important blocks are the OPC UA client and OPC UA server, and you just drag and drop these blocks into your model. You start your simulation, and you have got a client or respectively a server. Now here I've dragged a server component into my canvas, and in addition there is this nodes, which is actually a configuration record that is passed to the OPC UA server, and in this configuration record one can put in information about nodes which are created on the server during initialization. So nodes are the fundamental element of OPC UA. They can be identified by a node ID, and they can have attributes that allow to model all kinds of things. So in a very basic way, they can be so-called variable nodes. So they can contain as an attribute a variable of some type. That is used here at the bottom in this blocks. We have got this write double block and the read double block, and they read or respectively write variable nodes in the server's address space. Again, you can then just start this by simply simulating the model, and I almost forgot this lean logger init block, which simply is an optional block. It simply registers several functions to the external DLL so that logging output from the C side is redirected into the Modelica tool. Let's dive a bit deeper into the server example. If you double click on this right double block, then you get this dialog, and the first three parameters are for specifying your node. The first is the namespace index. So on the server, the nodes are organized into namespaces, so you need to get the right one. Then there are different types of identifiers that can be used for identifying a node. And one example is a string, which is used here. So we have got give it the value the dot double, but it can also be, for example, simply an integer value. Then these are sampled blocks. So we have got some activation conditions. It can be periodically activated by a sample time, or we can have we can enable an external trigger for this block. At the bottom, we have got this nodes configuration record, and if you double click on that, you get a flat list which allow you to specify some kind of nodes which are particularly useful in a Modelica simulation. On the left side, there's also the first three columns which specify information about the node. When you've got the display name and the description, those are interesting for browsing the address space. And then you have a data type, you have got array dimension and initial value. So that if this array dimension is like here, then it's a scalar, but you can put in arrays and matrices as well. Now you can start that and connect to it, for example, using a test client like UA Expert from Unified Automation, which is a great tool which can be downloaded for free. And then you connect to this and you get this address space overview. And that is organized in a tree-like fashion, very similar maybe to a file system. And you can cover your nodes that you have created here. So we find the display name here again in this address space. And that nodes can be drag and dropped into a data access view, for example, for displaying more attributes. Important attribute that is shown here is, for example, the value of the node. Okay. Now the client blocks were quite similar. The client needs to connect to a server, and for that it has an endpoint URL as a parameter which specifies something about okay, which protocol is used, where is the server, and at which port is the server listening. Since the rest is quite similar, I skip it because we have not much time. Now, for the technology stack, at the base of the project is a CMake-based build and test environment, and on top of that, there's a third-party library, the Open6251 open source C implementation of OPC UA, which is a complete technology stack, one should say, and it's really great project. You see that there's also a node-set compiler.py inside that. So why is that in a C library? Well, as I mentioned before, you can create your own information models, and these information models need to be saved in some format, which usually happens to be an XML format. And this compiler can take this XML formats and it generates C code from it. So at the end, you program against the C API. And that is what is done here now in this block. That is where's my library starting. You have got C++ code, which adapts the interface from this Open6251, which is rather low level, into an interface which is a little bit easier to interface from Modelica. Then since Modelica is the external function interface is only defined for pure C, the whole thing is compiled in a DLL on Windows or a shared object library on Linux and has a pure C interface, so that from the function layer we can then access from Modelica the C++ code. Now, this is the package where you can see several external objects, and you have got several functions which work on this external objects, and you can work with these functions directly, or you can use the block layer or combine them together. Now, to an application example from the DLR Factory for Future project, for which you can see the URL down there. It's a robot cell from DLRM, which is our sister institute, and it is synchronized with Modelica-based real-time simulation model, which you can see here in the upper top. That is from us, DLR, using the DLR OPC UA library for connectivity on the Modelica side. On the robot side, we have got an OPC UA server, which is programmed by Corbinian Nortenstein and Stefan Schneier. In the video that I will show, you also see CID data, which is coming from Oliver Eiberger and Timo Bachmann, and most importantly, my colleague Robert Reiser, who did do this Modelica application example model. And if you are interested in this kind of modeling, please see his talk, Object Manipulation Assembly in Modelica, on Thursday. Now here we see the robot arm moving, and at the top right corner, you see a visualization of the Modelica model. So Modelica model is a OPC UA client which connects to the robot, and the robot writes its process data into its OPC UA server, and the Modelica model can access the process data and updates its simulation with it. So you see some lag there. Here, Modelica model then simply mimics what the real robot does. Now, the main goal of this whole experiment was to find out whether we can work with OPC UA as an exchange format together. So that's why it's a communication technology, and that worked well. So on top of that, we are now building more comprehensive robotic applications. Okay, and to my conclusions. Myself, I started with no prior experience with OPC UA, but the first steps were quick and smooth thanks to the Open6251 project and this freely available test client. Both I can warmly recommend. However, it also turned out that the complete OPC UA standard and related tooling is really complex, so I made more moderate progress than I expected. And my future plans is to further extend the scope of the OPC UA library, particularly for enabling comprehensive robotic applications. So that's the main goal. And also to follow the efforts of standardization in the OPC UA OPC foundation regarding robots. So there's still ongoing work, and also regarding low latency communications, there's a push to bring OPC UA also in an real-time communication context that can be replace the field bus in some cases. Okay, then thanks for your attention, and I'm open for questions.